Good afternoon. We are Yale Studio, presenting our Architectural Technologies Capstone Project, Westbrook Village. Yale Studio is a 4-person team with a focus on community, affordability, and human-oriented design. The first member of our team is Yuto Hasegawa, who specializes in architectural design, building code analysis, and construction systems. Alicia Almazan brings design and technology experience from her previous architectural studies and work, and acts as an all-rounder for the team. Levi Hampton specializes in BIM software as well as modular building systems. Finally, Emily Nelson brings residential design expertise and a strong grasp on bylaw and building code. Westbrook Village is a mixed-use, transit-oriented development located on top of and around the Westbrook LRT station in southwest Calgary. The project's main focuses are providing amenity-rich, affordable housing options, implementing modular CLT systems, and promoting urban placemaking and streetscape activation in the area.
Westbrook LRT station is surrounded by the communities of Killarney, Roscarrock, and Shaganappi. The site is located west of downtown Calgary, south of the Bow River, and just north of 17th Avenue Southwest. The Westbrook area hosts a multicultural community with varied ages and income levels, for which we have also identified an increasing need for affordable and accessible housing. While the lots surrounding the station currently lie empty, several development plans have been explored and approved to introduce mixed-use commercial and residential projects, as well as recreational and urban infrastructure on the site. An outline plan and land use redesignation proposal made by Matco Development, as well as various documents approved and published by the City of Calgary, such as the 17th Avenue Southwest Streetscape Master Plan and the Westbrook Community's Local Area Plan, served as initial guiding design concepts for our project. Our own master plan departs slightly from this and splits the project into 4 tentative phases. For our Capstone project, we chose to focus on Phase 1, located on the southeast corner of the site and consisting of 2 6-story mixed-use towers close to the LRT station south entrance, as well as prefabricated row housing live-work units along 33rd Street Southwest.
Both parts of Phase 1 use modular CLT construction. CLT stands for cross-laminated timber and is composed of wood boards glued together at perpendicular angles at a minimum of 3 layers. We use CLT panels to create volumetric modular boxes. These boxes were based on standard truck measurements to be transported to site and stacked to create buildings. We chose these construction methods for several reasons. 1. Modular systems reduce on-site construction time and community disruptions. 2. Given the scale of our project, modular systems can benefit from economies of scale. 3. CLT is well suited to creating rigid structures, which is important when transporting and assembling modular units. 4. Our group was interested in exploring alternative building systems.
Phase 1A consists of 3 blocks of row housing along 33rd Street Southwest. The row houses enclose the site, creating a street wall extending along the eastern edge of the property, while providing access into the site via 2 breezeways on the sides of each block. There are a total of 16 row house units, with private garage access on the west facade via a paved road behind the properties. Keeping with the module systems, the row house floor plans were designed to contain everything within a rectangular shape for ease of building, transportation, and construction. The designs of these plans were inspired by a floor plan by Sloker Homes. These floor plans were applied to the initial design and were adjusted to meet the requirements for modular construction. The units are divided into 2 unit types to accommodate for the different spacing of the CLT walls. When designing the CLT panels sizes for the module systems, we came across an issue with the ground floors of the row houses. Garage floors are required to have a minimum slope and displacement from the main floor according to Section 9.35 of the Building Code. Because of this, we were not able to create proper modules for the ground floor of the row houses. To solve this issue, we decided to use a prefabrication system for the ground floors while still using CLT panels. We decided to keep the module systems for the remaining floors of the row houses. A modeling challenge we wanted to take on was modeling the row house roof trusses. We wanted to learn how trusses are properly made, as well as how they look when proper measurements and spacing are applied. To achieve this, we used the Structural Truss tool in Revit to efficiently model the roof trusses in 3D. This way, we would not have to manually draw each truss. This completes the construction of Phase 1A.
Moving on, Phase 1B consists of 2 mixed-use apartment buildings connected by an elevated walkway. The north tower lies parallel to the northern edge of the lot, while the south tower follows a 60-degree angle in response to the observed pedestrian circulation tendencies of people moving between the entrance of the station and the corner of 17th Avenue Southwest and 33rd Street.
The North Tower contains the lobby, residential units, and amenity spaces, as well as gym, laundry, and daycare facilities along the proposed new street. The lobby faces Westbrook Station, emphasizing our project's connection to sustainable transportation. This connection is reinforced by absence of underground parking and extremely limited surface parking. The South Tower contains residential units oriented 60 degrees south-southwest. This angle reduces wind tunnel effect in the enclosed outdoor space and places building perpendicular to the SAIT slope. Because of this slope, the South Tower is constructed partially below grade on concrete pedestal. After the foundations are poured, steel framing construction will begin on the North Tower to build the lobby, communal spaces, and daycare areas. The main reason why we used concrete instead of steel structure in the South Tower was so we could reduce the amount of beams and columns inside the commercial rental units, not only simplifying the structure but also maintaining a more than comfortable floor-to-ceiling height. After the shared areas are completed, modular boxes will be stacking on top of each other. The biggest ideas when we were discussing about modular boxes' shape was how repetitive they can be placed. So both studio and living areas of 2-bedroom units are made out of the same box types. 2 modular boxes for general use and 1 sanitary box for bathroom. By simply adding 2 of another box type, studio units become 2-bedroom units.
These are some notable design challenges we found while working on this part of the project. Just like we've already mentioned, a concrete transfer slab was needed between the first 2 floors of the building. Y-shaped concrete columns on the exterior support the overhangs from the modules resting on top of the slab. We initially thought the cladding from the upper levels would be interrupted when it reached the transfer slab, but once we started adding details such as soffits, we realized we needed to reduce the podium's outline so that the insulation and cladding could be dragged down and then wrapped around the slab to connect to a soffit. This became an issue in certain parts where reducing the slab meant the top of the window walls would become exposed. We solved this by creating secondary grid lines to move most of the storefronts and structure on the ground floor's perimeter around 500 millimeters inwards, so that these elements remain contained between the floor and podium slabs without clashing with any other components.
This detail shows the connection between the concrete balcony and the CLT apartment units. A prefabricated concrete slab will be held by a 310 by 512 mm steel angle. We provide a 128 mm gap between the CLT structure and balcony to prevent thermal bridging.
This detail illustrates how the modular boxes connect together and interact with exterior cladding systems. Tension rods are used at the corners of modular boxes to add rigidity and hold the modular units together when assembled. At the inside corner, additional membrane is added to ensure continuity of the building envelope. This membrane consists only of an air barrier, as vapor barriers can trap moisture in the CLT structure and impede its natural ability to dry.
For cladding, our goal was to use materials that are environmentally conscious and durable while achieving a modern aesthetic. We settled on using brick, composite aluminum metal panels, Calzip standing seam cladding, and corrugated steel. All 4 materials are highly durable and will last for several years with little need for maintenance. We decided to look into HVAC, plumbing, and electrical systems to learn more about how they work and how they may affect the overall structural design of both the modules and row houses. A challenge we encountered was orienting all 3 systems with the CLT panels. A CLT panel should not be cut into unless necessary. Since all 3 of these systems traditionally rely on stud walls in either beam or I-joists in order to conceal them, designing the orientation of the HVAC, plumbing, and electrical became essential in determining if having CLT module and prefab systems would properly function well. We were required to add additional stud walls to some of our CLT walls in order to provide more space for electrical wiring and outlets. The HVAC and plumbing was designed to be against the walls as much as possible to avoid affecting any headroom issues. This detail highlights the results of exploring the HVAC, plumbing, and electrical systems. Both walls and floors were modified to accommodate these systems. A partition wall was placed underneath the CLT to accommodate electrical wiring and fixtures, and finished with gypsum board. The second floor walls received an additional 2x4 partition wall and gypsum board to accommodate mechanical and electrical systems.
Overall, we think the Westbrook Village project fulfills our goals of affordability and urban placemaking, while making use of alternative construction methods and materials. With this project, we learned about multiple construction systems and building types. Additionally, we learned to streamline collaborative work and communication over the course of the semester. We would like to thank our instructors for their support during this project and our classmates at SAIT for creating a rich learning environment. We would also like to thank the audience for their time and attention as this concludes our presentation.